So module 5 single phase AC motors. Module 5 single phase AC motors. Single phase AC motors are classified into single phase induction motors, universal motors, repulsion motors. Among these, single phase induction motors have more importance than that of the other two. So in this module we are going to discuss about single phase induction motors. So single phase motors are classified into three: single phase induction motors, universal motor, repulsion motor. Among these, single phase induction motors are much significant. Single phase induction motors work on single phase AC supply, and these are the most widely used motors in houses. Single phase induction motors are working on single phase AC supply, and these are the most widely used motors in houses. Single phase induction motor has a squirrel cage rotor and an ordinary stator which consists of a single phase winding. Okay, it has two parts. A single phase induction motor has two parts, stator and rotor. Stator consists of single phase winding. Stator consists of single phase winding, and rotor is a squirrel cage rotor. Rotor is a squirrel cage rotor, and stator consists of a single phase winding. Single phase induction motors are not self-starting. Why? What's the reason for that? When we give single phase AC supply to the stator winding of a single phase induction motor, when we give a single phase AC supply to the stator winding of a single phase induction motor, a magnetic field is developed in the stator, which is an alternating one. Only a rotating magnetic field can rotate a stationary squirrel cage rotor. Only a rotating magnetic field can rotate a stationary squirrel cage rotor. Here we are giving single phase AC supply to the stator of an induction motor. Then an alternating magnetic field is developed. Only a rotating magnetic field can rotate. Only a rotating magnetic field can rotate a stationary squirrel cage rotor. Therefore, single phase induction motors are not self-starting. Okay. However, if the rotor of a single phase induction motor is rotated in one direction by some mechanical means, it will continue to run in the direction of rotation. It will continue to run in the direction of rotation. Suppose we start the motor by using some mechanical means, it will rotate. Otherwise, it cannot rotate because an alternating magnetic field is developed in the stator when the stator winding is fed from a single phase supply. Only a rotating magnetic field can rotate a stationary squirrel cage rotor. Then what is the solution for making a single phase induction motor self-starting? It is necessary to self-start the induction motor. For that, we are adopting different methods. That methods we are going to discuss in this class. So first important point, you have to understand that single phase induction motors are not self-starting because an alternating magnetic field is developed in the stator. It is necessary to convert the alternating magnetic field into a rotating magnetic field. It is necessary to convert an alternating magnetic field into a rotating magnetic field. To make a single phase induction motor self-starting, it is necessary to produce a rotating magnetic field. This may be achieved by converting a single phase supply into two-phase supply through the use of an additional winding known as starting winding. Okay. Thus, the induction motor consists of two windings. The induction motor, stator of an induction motor consists of two windings. One is known as main winding or running winding. Other is known as starting winding. One is known as main winding or running winding, and other is known as starting winding. Thus, there are two windings in the stator: starting winding and running winding. Starting winding is only for starting period. It is to produce a rotating magnetic field in the stator. By using a single winding, we cannot produce a single winding cannot produce a rotating magnetic field. Single winding can produce only an alternating magnetic field. To convert that alternating magnetic field into a rotating magnetic field, an additional winding is provided in the stator known as starting winding or auxiliary winding. Starting winding or auxiliary winding. When the motor attains sufficient speed, we can electrically cut off. When the motor attains 80% of its rated speed, we can electrically cut off the starting winding. From the stator. Thus, under normal running condition, its stator consists of only one winding. Under normal running condition, its stator consists of only one winding. Then classification of single phase induction motors. Classification of single phase induction motors. Single phase induction motors are classified into two: split phase motors and capacitor motors. Single phase induction motors are classified into two: split phase motors and capacitor motors. Split phase motors split phase motors are started by a two-phase motor action through the use of an auxiliary winding or starting winding. What about capacitor motor? These are started by a two-phase motor action through the use of an auxiliary or starting winding and a capacitor. That means in the case of split phase motors, its stator consists of starting winding and running winding. But in the case of a capacitor motor, its stator consists of a running winding, starting winding and a capacitor. The capacitor is connected in series with the starting winding. Capacitor is connected in series with the starting winding. So two types of capacitor motors are there: capacitor start motor, capacitor run motor. Two types of capacitor motors are there: capacitor start motor, capacitor run motor. Okay. Then first one, split phase induction motor. Split phase induction motor. Split phase induction motor, the stator of a split phase induction motor consists of two windings. One is main winding or running winding represented as M, and other is starting winding represented as S. The two windings are connected in parallel. Rotor is a squirrel cage rotor. Rotor consists of a squirrel cage rotor. Stator consists of two windings: main winding and starting winding. Main winding or running winding. Main winding running winding, and the other is a starting winding. Main winding or running winding, and the other is a starting winding. A capacitor is connected in series with the starting winding. Okay, the two windings are connected in parallel. After that, we are giving an AC supply to this parallel combination. Then what happening is the current split into two. One current is passing through the starting winding and other current is passing through the main winding. Main winding is an inductive winding because it has low resistance and high reactance. Main winding is an inductive winding because it has high reactance and low resistance. Starting winding consists of high resistance and low reactance, so it is considered as a resistive circuit. So two windings have two different electrical characteristics. Main winding is an inductive circuit. Starting winding is a resistive circuit. The two windings are electrically displaced by an angle difference. It is approximately about 25 to 30 degree because starting winding through the starting winding current is almost in phase with the voltage. But in the case of main winding, current lags the voltage by a large angle. So see the figure on the right, see the phasor diagram on the right hand side. IS lags V by a small angle because it is a resistive circuit. IM lags V by a large angle because it is an inductive circuit. IS is almost a resistive circuit, therefore it lags V by a smaller angle. IM lags V by a larger angle. IM lags V by a larger angle. IS lags V by a smaller angle. Anyway, there is an angle difference of alpha between IS and IM which is of almost 25 to 30 degree. Okay. Thus, a rotating magnetic field is developed in the stator. Okay, even though we are giving single phase supply, the given single phase is split into two. A part of the current is flowing through starting winding represented as IS, and the rest of the current is flowing through main winding IM. I is the vector sum of IM and IS. I is the phasor sum of IM and IS. IS lags V by a smaller angle because it is a resistive circuit. IM lags V by a larger angle because it is an inductive circuit. Anyway, there is an angle difference of 25 to 30 degree between IS and IM. Thus, two phases are flowing in the stator. The given single phase is split into two. So two phases are flowing. Therefore, a rotating magnetic field is developed in the stator. So in this manner, we are converting the alternating magnetic field into a rotating magnetic field. We are providing an additional winding in the stator. The existing winding is main winding or running winding. It is an inductive circuit because its resistance is very low comparing to reactance. Therefore, it is an inductive circuit, but starting winding consists of a resistive circuit because it has larger resistance. So there is an angle difference of 25 to 30 degree between IS and IM, which is denoted as alpha. Angle difference between IS and IM is alpha, which alpha is about 25 to 30 degree. Thus two phases are flowing in the stator. The given single phase is split into two. So with the help of a starting winding which has high resistance and low reactance, we can split the single phase into two phase. A two phase supply can produce a rotating magnetic field. Two phase supply can produce a rotating magnetic field. Okay, when this rotating magnetic field is developed in the stator, when a three phase winding or we know that a three phase winding is fed from a three phase supply, a rotating magnetic field is developed in the stator. The same way, even though this is not a we are not giving three phase supply, we can create a polyphase supply here by splitting the single phase into two phases. A rotating magnetic field is developed in the stator. This rotating magnetic field passes through the air gap. This rotating magnetic field passes through the air gap and cuts the rotor conductors according to Faraday's first law of electromagnetic induction. According to Faraday's first law of electromagnetic induction, this magnetic field, thus, as the rotor is a squirrel cage rotor, a current circulates through it known as eddy current. This eddy current opposes the rotating magnetic field in the stator. This eddy current opposes the rotating magnetic field in the stator, but the opposition exerts on the rotor itself. And the rotor starts to rotate in the same direction of magnetic field, but not at the same speed. Rotor rotates in the same direction of magnetic field, but not at the same speed. Okay, in the same direction of magnetic field but not at the same speed means this motor is rotating at a speed less than synchronous speed. This motor rotates at a speed less than synchronous speed. After developing a rotating magnetic field in the stator, this rotating magnetic field passes through the air gap and cuts the rotor conductors, and an EMF is induced in the rotor according to Faraday's first law of electromagnetic induction. Okay, as the rotor is a closed circuit, a current circulates through it known as eddy current. This eddy current opposes the rotating magnetic field in the stator, but the opposition exerts on the rotor itself, and the rotor starts to rotate in the same direction of magnetic field, but not at the same speed. Okay, it is rotating the same direction of magnetic field but not at the same speed. Thus, a split phase induction motor is also running at a speed less than synchronous speed. This is the working of a split phase induction motor. Okay, so all these things I discussed in this session, how a single phase induction motor starts to rotate. Okay.